Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by the Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar lecture theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, welcome to the next lecture on the course Maritime Structures, Types, Construction, Pre-Service Analysis and Design. This is lecture 5. Which is going to be on floating structures part 1. So friends, we already saw the structural action of different kinds of structures which are enabled by the geometric form as they are commissioned at different water depths. We have realized that the structural action offered by these structures are not uniform. Some of them offer resistance by the strength and stiffness, by the virtue of their rigidity. Some of them offer resistance by relative displacement of the system as a rigid body motion. When the system is allowed to completely float, which is not compliant but fully floating, the substructure component of the system is by and large absent. So now friends, imagine the cost saving what one gets from a floating structure with respect to a fixed structure. In a fixed structure, as we understood, the substructure component may be gravity based structure, which is concrete caissons, or jacket structure, which is steel structural members, or jack-up rigs, which is again steel members. A phenomenal cost of material and design and complications in construction gets entangled in these kind of structures, as a huge amount of material is invested in the substructural form in these structures. Whereas, when the structure is kept completely floating, the substructure concept or the money spent on substructure part is completely saved, friends. So, I can simply use a vessel which can be transported or towed from one location to another location. Wherever we get oil, we can use it for exploration. So, the versatility of using a floating structure is much higher compared to a fixed or a compliant structure, because these structures, fixed and compliant, are position restrained either by pile foundation or by cables or tethers or spud can systems, whereas floating structures are not position restrained. They can float and remain to float and remain to sail wherever they want to do so. The best example of a floating structure could be a drill ship, it can be a semi-submersible, it can be an FPSO, and so on. So now, as these type of structures are more fascinating and more advantageous, and they are useful for ultra deep water oil and gas explorations, it is mandatory that we try to look at these structures, the design of them and the geometric form of these structures more in a closer window. So, this lecture will enable you to help understand the floating structures slightly more in detail. These are some of the reference books which I want you to follow. These books are available in IIT Gandhinagar and other IIT libraries as a virtual copy or a e-book. Can access them on request if you register for this course in SwayamPrabha, Dynamic Analysis and Design of Offshore Structures by Springer, Reliability and Risk Assessment of Offshore Structural Engineering by CRC, Advanced Marine Structures CRC, Ocean Structures, Construction, Material and Operation again by CRC, Health, Safety and Environmental Management of Offshore and Petroleum Engineering by Wiley, Offshore Semi-Submersible Platform Engineering by CRC, Structural Health Monitoring with Application to Offshore Structures by World Scientific Publications Singapore, Design Aids for Offshore Topside Platforms under Special Loads by CRC, Offshore Compliant Platforms by Wiley, Design of Marine Risers with Functioning Graded Materials by Elsevier. These are some of the interesting textbooks for additional reading which I strongly recommend to you, so that you also enhance, strengthen your learning skills by following these books. However, if you are also a faculty following this course from an institution, please keep a copy of these textbooks in your library and improve the capacity building of yourself and your research scholars and students in the maritime sector. As I told you in the beginning of this course, maritime engineering is going to have a lot of job opportunity coming in way in a very near future. Having said this, let us talk about more detail on compliant and floating structures as an enhanced value of compliant structures. So now let us talk about the compliancy and floating characteristics. We have already saw that the structural forms of compliant and floating structures are different from fixed, and they are conceived to counteract the applied loads acting on them not by strength but by geometry. So, I can now say very clearly compliant and floating structures are classical examples of form dominant design. Maritime structures are designed to counteract the loads through these innovative geometric forms, and they resist the forces not by strength of the material alone, but they resist them by the geometric form. So, the resistance or the structural action of compliant and floating structures essentially comes from a major sector, which is from the geometry. The moment I say geometry constrained design, one has got to be very careful in choosing this geometry. If you make any mistake in the design of choosing this geometry, which can offer resistance, then the whole structure can capsize. Whereas this cannot and need not essentially happen in fixed based structures, because they resist the forces by strength of the material and the size of the members. Whereas here, apart from the material strength, they resist the forces by arrangement of members. So, what is form dominant design? Form dominant design essentially talks about arrangement of structural members, their connections, in addition to the material strength and support conditions, sizing of the members. So, these two components are additional to what you already have in strength based design. Okay. So, the form dominance, which is essentially necessary for a compliant structure and a floating structure, comes from these two additional points what you see here. Having said this, let us see what are the factors that influence the geometric form choice. The geometric form what you choose should be a stable configuration. It should lead to very low installation cost, fabrication cost and decommissioning. Together, it should attract very low capex. Capex stands for capital investment. OPEX stands for operational cost. So, form dominant designs should be chosen in such a manner that capex is as minimum as possible. Okay, it should have a minimum capex. The geometric form should result in early start of production and should possess high mobility. So, let us note down the points: low capex, high mobility, early production start, therefore, can give you quick return on investment. This is a very interesting financial factor. So, for example, if we invest, let us say 100 crores today, when will you get back this 100 crores? With interest for the period. This is what we call this period is called return on investment. So, if you are investing a huge money to construct a platform, then the platform has got to produce oil and the oil has got to go to the commercial market to get you the revenue. What would be the return time within which you will earn your capital with interest and of course with certain profit? Okay. So, this is an important factor which every investor looks at it. Why not in maritime engineering? So, return on investment should be very fast. It should yield you very high return on investment. So, the geometric form should have all these advantages when you choose a form. So, the design of floating structures is essentially not only limited to structural engineering. It is limited to architectural form which you choose to counteract the forces and to also make it workable and practically viable for the functional use of the platform. So, therefore, the geometric form should require least intervention. You should not carry out repairs very often in the geometric form, because any repair carried out on a structural system in maritime engineering will cause you something called downtime. Downtime is the time within which the platform remains non-operational, no oil is produced. We already saw in the previous lecture that what would be the revenue of one single platform in terms of Indian rupee in the current market value. So, the downtime should be minimum. To minimize the downtime, one should always make interestingly the observation that the platform or the geometric form should have very least intervention so that the production is not interrupted. So, the production remains uninterrupted. So, the revenue from the platform is constantly increasing. So, one can see these factors are far different from engineering perspective of a structural design. So, design of a compliant platform or a floating platform does not confine only to finding out the member sizes and strength of materials. Here the design is extended beyond the table and saying that it is going to have a low capex value, a very high mobility. The platform should be able to move from one location to another location like drill ships, semi-submersibles, FPSOs, etc. High mobility, very high return on investment, low capex and minimum opex and no interruption during the function of the platform. These structures should remain insensitive to lateral loads. That is very interesting. So, it means you should be able to operate the structural system or these platforms. This platform should remain operable in all sea states. For example, if the wave height is very high, it can land up in sort of a tsunami. So, we are not saying that this platform should operable in tsunami, but the platform should not fail structurally even at very high sea states. So, the platform should remain stable. Okay? So, the failure should not happen and the platform or the structure should remain insensitive to lateral loads. We also know from the previous lecture that compliant platforms resist encountered loads both from the material strength and structural redundancy, what we call as a form dominant design. Therefore, a strength-based design approach which results in very low displacement and lateral loads cannot be directly applied to these kind of platforms. So, the form dominant design which inherently supports, promotes, accepts large displacement should have a different perspective of design compared to strength based approach. So, we are now talking about the flexibility property helping to counteract the loads that will happen only when you enable large rigid body motion on the platform. So, the large rigid body motion on the platform which is helping you to counteract the loads should also be taken care of when you do the design of these platforms. Okay? So, the design perspective gradually is changing from a strength based approach to displacement or rigid body motion based approach. We call this concept inherently as form dominant design approach. Friends, should you have any questions in between the lectures, note down on a piece of paper and please email to us at SwayamPrabha. We have a discussion forum enabled when this course is promoted. You register for this course and you apply these questions through an email and you will get a reply 24/7 by the instructors and the TAs running this course. So, SwayamPrabha is a motive media which helps you to strengthen your learning informally by better lecture approaches and practical applications on novel topics which is also being taken care of in Maritime Engineering Department at IIT Gandhinagar. So, now we learn that complaint platforms are permitted to undergo large displacements. Then, how do you stop them leaving its equilibrium position? So, we now say when you allow the platform to undergo large displacement, you must also ensure the position keeping by something called recentering. So, usually complaint platforms are position restrained either using cables or tethers. For example, TLP is a tether restraint system which activates recentering by the horizontal component of the forces what is offered by the tethers. To recollect it, we can again draw a TLP. If this is my seabed, this becomes my mean sea level, this is our water depth. When the platform moves to the right, the T0 offered horizontally will bring the platform to its equilibrium position. We call this process as recentering. So, when you allow large displacements, rigid body motion happening on the design, then the platform should also be checked for its recentering ability. For recentering, we should not invoke any external forces. It should automatically happen by the design. That is a very important requirement. Let us write down here. Recentering should be invoked by the design itself and not by applying any active or passive external controls. Okay? It should happen within the design itself. Recentering is an inbuilt phenomenon. No external agency. Remember that. Okay. Therefore, these platforms resist loads. In addition to the material strength, the major contribution comes from the relative displacement concept of design what we otherwise said as form dominant design. Complaint platforms do not resist loads because of fixity to the seabed. Remember that we are talking about floating structures where the substructure part of the system is relatively absent. So, there is no fixity of these platforms to the seabed. Therefore, the support conditions do not offer resistance to this. Can you give me an example where the support condition offers resistance to a lateral load? That is a very interesting question posted. Let us quickly revisit how the gravity based platforms resist loads. We have a gravity based platform, we have caissons, because of the colossal weight, caissons rest on the seabed and they offer very good resistance at the seabed. So, the lateral forces are acted or counteracted by these resisting components. Okay. So, when a fixed base structure like GBS could resist forces by the friction offered by the contact pressure between the structure and the soil, if we have a floating structure where the substructure is completely empty, missing, then this reaction offered is also missing. Then how the resistance is happening? The resistance has to happen based upon the recentering ability and flexible capacity of the platform. So, therefore, friends, complaint platforms and floating structures do not resist loads by their fixity to the seabed. In fact, they resist loads more by their motion characteristics. Therefore, dynamic design or dynamic analysis and design becomes very important for these kind of structures. Having said this, now let us look at the summary of what we are talking about in floating structures in general. Complaint platforms, which is also a part of a floating system. Floating system does not have substructure, but complaint structures have a substructure like tethers or wires or guy wires or ropes. So, complaint platforms are position restrained by cables or tethers. Okay. Now, let us have an idea about the value of this. Let us say I draw a TLP, fix it to the seabed. Now, I am marking the water level. We know this is the depth of the water indicated as D. These elements are called as pontoons. These elements are called as column elements and this is the deck. I can even draw them thicker, column elements, pontoon elements, and the deck will also have the superstructure facility, the flare boom, the drilling derrick, the helipad, etc. Okay. Now, we already said that if weight is acting downward and the displaced volume will improve buoyancy, it acts upward. So, weight is acting downward, buoyancy acts upward, and we already said it is the positive buoyant system. Therefore, buoyancy exceeds the weight. So, the platform floats. Okay. What is the difference? Let us say buoyancy acting upward should be equivalent to weight acting downward plus something. This something component is T0, which is the axial tension in the tethers. So, this difference between FB and W is about 15% of mass. To give you an idea, the mass of a TLP is about 80,000 tons. Huge number, friends. In Newton or in kg, you will be keep on counting zeros. It's a huge number. So, 10 to 15% of that value is my T naught. So, the axial tension offered by the ethers was very high. They are very high. Okay. Therefore, when the TLP moves to the right, the horizontal component of this with a huge number tries to pull back the TLP to its equilibrium position. We call this process as recentering and this motion as TLP mechanics. This is called offset and this is called set down. Okay, let us go back and we understand that large pre-axial loaded tethers offer resistance lateral loads and they will enable recentering of the platform. Therefore, the design has now shifted from strength based concept to displacement control design. Okay? So, the design phenomena of offshore or maritime systems has been moved, transformed from strength based concept to displacement control design. Large displacements are allowed in the design because I want the platform to remain flexible. When I allow large displacements in the design, I must then ensure recentering ability of the platform. So, recentering ability should be an inbuilt phenomena in the design as a part of the design and it should not be an external component offering additional force to bring recentering of the platform to attain its equilibrium position under the action of forces. So, recentering should be inherently a part of the geometric design itself. That is what you see in guide towers, articulated towers and TLPs. Recentering is an extension of elasticity. We already compared elasticity and recentering clearly. So, it is very important that in offshore compliant platform design, large displacement should be enabled. If you enable large rigid body motion, then recentering should be a part of the design itself, which should happen within the platform design. Let us now make quickly a summary. So far, what we have learned? In floating structures, we understood that the substructure component is grossly absent. Therefore, floating structures do not resist forces by support offered by the seabed, because they do not rest on seabed at all. Then how do they do? They resist forces by the relative motion. I put a apostrophe and relative motion, okay, between waves and the structure. So, this phenomena is very interesting. We call this as fluid structure interaction. So, this now becomes an additional feature of design in compliant and offshore structures and floating offshore structures, which is not a very important component in fixed platforms because the displacement offered by fixed platforms are very minimum. In addition, since we are allowing large displacements, in compliant platforms and floating structures, we should ensure that these platforms enable recentering. Recentering is an ability of the platform to attain its dynamic equilibrium position in the presence of forces. It is not material property. It is a geometric property. Therefore, the structural design of compliant and floating platform should enable recentering automatically, friends. It should not be done by any external or additional forces. So, the geometric design itself should enable this recentering. So, friends, in this lecture, we try to cover the structural action more in detail about compliant and floating offshore structures, and we already know that offshore structures are a subset of maritime structures. So, friends, we already said for additional reading, please refer to the textbooks cited in the SwayamPrabha website. You can also have an virtual access to these books from IIT Gandhinagar and IIT's library if you register for this course in SwayamPrabha and try to learn more information from these textbooks, discuss them in the discussion forum, put your questions, interactively remain connected to the instructors so that you get the best benefit when you learn this course along as we teach this course. Thank you very much. Namaste.